Hello everyone. On this video we will be going over our Lagrange multipliers. Okay, so to start off, let's say if we start with an ellipse. Okay. So if that ellipse is just x squared over 9 plus y squared over 16 equals 1. Okay, so what if we just rewrite it to x squared over 3 squared plus y squared over 4 squared equals 1. Okay, so nothing really out of the ordinary about that one. Okay, we just have a regular ellipse. But what if we wanted to find the maximum area of a rectangle that could fit in that ellipse? Okay, so what if your goal is to find the maximum area of a rectangle that could fit inside that ellipse? Okay, so we're just going to draw an ellipse with a rectangle inside. Okay, so first I'm going to draw the rectangle, then I'm going to draw the ellipse. Simply because it's easier for my artistically challenged brain to do that. Okay, so if we draw the ellipse, oops, it's a little bit wider than I wanted to draw that one. Okay, because it has to hit all 4 corners. There we go. Now we can finish drawing x and our y. Okay, so we have a rectangle, and we want to know exactly the largest area we could fit inside of that ellipse. Let's say this corner right here, that's our x, comma y. Okay, so where our x, y is our vertex in quadrant 1. Okay, now starting off, we see here that this length, that's your x, and from here to here, that's your y. Okay, now to find the width of the entire rectangle, you have x plus x. So the whole width of the entire thing would be 2x. So, since the width equals 2x, and length, okay, remember the length is y plus y. These should be both the same length, but I didn't draw it the same length, so let's just assume it's the same length from here to here. So you have y plus y is 2y, so the length equals 2y. Now that means the area equals length times width. Remember, that's the area of a rectangle. We have our length times width. In other words, it's 2x times 2y, which is 4xy for our area. Okay, so our area, remember, we want to look at the maximum area of that rectangle. So we'll let our area be a function f of xy, which is 4xy, and we'll call that our objective function. Okay. Now remember, that rectangle is constrained inside of our ellipse. So we'll make g of xy equals x squared over 3 squared plus y squared over 4 squared equals 1, our constraint function. All right, let me move that up. Okay, now, what we're going to do, instead of focusing on the entire thing, we're just going to look at quadrant 1. Okay, so I'm going to just separate that a little bit. So if we look at quadrant 1 only. Okay, so that means if we look at just quadrant 1, we look at the 1/4 of that rectangle and bit of that ellipse. Or if that's our x, and that's our y. All right. Now, if we are looking at our tangent vector at that particular point, we know that our tangent vector, let's say that's go down there, we know that our gradient is perpendicular to that tangent vector. Okay, so our gradient, we'll call that our delta of f, or delta f of xy. Okay, now with that gradient vector, the one thing we have to remember is it's going further and further out, but at the same time, it's being constrained in the opposite direction. So let's say if that opposite direction we want to look at, we'll just put a parabola there to kind of be our tangent of our hyperbola. Okay. Now, one thing we can look at and say, okay, we have our gradient of f. You look at our hyperbola. Let's say in that hyperbola, in the exact same spot, we could have another gradient. We'll say the gradient of that hyperbola is the gradient of g of xy. Okay, now it doesn't have to be the same size. It can be smaller, it can be longer. We just know that it's a multiple, a scalar multiple of it. Because for them to be parallel, they have to be scalar multiples of each other. That's just how vectors work. Okay? Now, if they're scalar multiples of each other, that means that the gradient of f of x, y, has to equal some scalar multiple, which throughout mathematics, they usually use lambda in this case, scalar multiple of gradient of xy. Now that scalar multiple is called the Lagrange multiplier. The scalar multiple lambda, I think it's L-A-M-B-D-A, I think, I don't know. You might want to double check the spelling. I hardly ever think it's lambda. But that is the scalar multiple that you can use. Alright. and that is called your Lagrange multiplier. Okay. All right, now what that is going to do is that's going to lead us to our Lagrange theorem. All right, so if you are still writing, feel free to press pause, but we're going to go ahead and move on to our next page. Okay, so the theorem, Lagrange's theorem. Okay, I'm pretty sure he has a gang of theorems to his name, but this just happens to be the one for the multiplier. Okay, so let f and g have continuous first partial derivatives. Such that f has an extremum at the point x0, y0. Finish up. On the smooth constraint curve. That we will call g of xy. And that g of xy will equal c. Okay. Now, as long as we know that our g of xy, x0, y0 doesn't equal a zero vector, so if the gradient, we got the little gradient symbol, the gradient of g of x0, y0 does not equal the zero vector, then there's a real number lambda is a real number that we will call lambda, such that the gradient of f at x0, y0 is equal to lambda times the gradient of g of x0, y0. Okay. All right. Now, there are a few steps that you can follow to help you apply Lagrange's multiplier to find out the minimum or maximum of your gradient. All right, so the method of Lagrange multiplier, and we will follow those steps in the example, so don't be too worried if it doesn't make sense immediately. Okay, so what if we let f and g satisfy the hypothesis? The hypothesis of Lagrange's theorem. Okay, so in other words, this part up here, your Lagrange's theorem, all of that is met. Okay. In addition, what if we let our f have a minimum and maximum subject to the constraint of our g of xy? So we'll let f have a minimum and maximum subject, let me clean that up a little bit. So it's subject to the constraint of g of x, y equals some constant c. Okay. So to find the minimum and maximum, we just follow these steps. Okay. Now your first step is you want to solve the system of equations f of x, well, f partial f with respect to x is equal to the lambda times the partial g of x with respect to, well, g with respect to x. 2, you want to find the partial with respect to y is equal to lambda times the partial of g with respect to y. And your constraint g of x, y is equal to c. Okay, so you want to solve all of those. Okay. 2, you want to evaluate your function f at each solution point. From the first step. Now, once you evaluate them, you have the largest value, that will be your maximum, and the smallest value will be your minimum. Okay, so the largest value is the maximum of f. So the maximum of your f, move that up a little bit, subject to the constraint. And our constraint, in case you forgot what the constraint was. Also, the smallest value is the minimum. Of our function, subject to the constraint. G of x, y equals c. Okay, so whatever that constraint is, our f value will be the maximum or minimum. All right. So if you are still writing, feel free to press pause. But we're going to go ahead and jump to our first example. Okay, so for example, if we wanted to find the max value of f of x, y equals 4 xy, where x is positive and y is positive, subject to the constraint of x squared over 3 squared plus y squared over 4 squared equals 1. All right, so first thing you're going to do, you're going to find your gradient of your objective and constraint functions. Okay, so the gradient, let me write that out actually. Find the gradient, not 2, of your objective and constraint functions. All right. I can focus that a little bit better. There we go. That's a little better. Okay, so your gradient, you remember, of f is equal to the partial of f with respect to x times your I vector plus the partial of f with respect to y times your j vector. Okay, now the partial of f with respect to x is actually just 4y. So you have 4y times your I vector plus the partial of f with respect to y is 4x. So you have 4x times your j vector. Okay, remember that's your objective function. Now we find your gradient of g. Okay, but remember, we're not looking for your gradient, we're looking for lambda times your gradient. Okay, so that's going to be lambda times partial of g with respect to x times your I vector plus the partial of g with respect to y times your j vector. Okay, so that's going to equal lambda times your partial of g with respect to x is 2x over 9. So you have lambda times 2x over 9 times your I vector plus lambda times the partial of g with respect to y. That would be 2y over 16, which actually simplifies to y over 8. So y over 8 times your j vector. And that's your constraint function. Okay, so far, so good. Okay. So now what we're going to do is we're going to do all of our steps. So our method steps, we're going to do those one at a time. All right, so if you remember, you have partial with respect to x of f, which is lambda partial with respect of g to x. You have the partial of f with respect to y equals lambda times the partial of g with respect to y. And you have your constraint, which is g of xy equals c. Which is your constraint. All right. Now, the partial of f with respect to x, remember that's 4y, equals lambda, and your partial of g with respect to x, remember that's 2x over 9. You have your partial of f with respect to y. Okay, so if you remember, that's 4x. And your partial of g with respect to y, remember that's y over 8. So you have lambda times y over 8. And your constraint, remember that's x squared over 3 squared plus y squared over 4 squared. Okay, so x squared over 3 squared plus y squared over 4 squared equals 1. Okay? That's your constraint. Okay? Now, what we're going to do here, we're going to solve for lambda and plug into the second equation. All right, so what we're going to do is we're going to go ahead and do that right down here. Okay, so if we solve for lambda, just multiply both sides to 9 over 2x, and you end up with lambda equals 18y over x. Okay, then we're going to get that and plug into the second equation. All right. So since we have our second equation here, replace that with lambda. So that gives us 4x equals 18y over x for our lambda. 18y over x times y over 8. Okay, now once we plug that into there, the next step would be to solve for our x squared. Solve for x squared and plug into the third equation. So really the overall goal was to get rid of the lambda by the time we reach the third equation. So by the time we get to the third equation, the lambda should be gone. And you should be down to just really one variable. Okay. So if you simplify here and solve for x squared, you see that x squared is equal to 9 over 16 y squared. All right, then from there, we just plug into the third equation. All right, so we have our third equation here. We have x squared over 3 squared, or x squared over 9. So we're just going to factor out that 1 over 9. And x squared will just become 9 over 16 y squared. Plus y squared over 4 squared equals 1. Okay, so the two 9s will cancel out, so you end up with y squared over 16. So you have y squared over 16 plus y squared over 16. So that's y squared over 16 and y squared over 16 equals 1. So you get 2y squared over 16, multiply by 16, divide by 2, you get y squared equals 8. Square root both sides, you have y equals plus or minus 2 square root of 2. Okay. Now remember from the beginning, scrolling up for a minute, y is greater than 0, so we're only going to use the positive. Okay. So y is greater than 0, so y is equal to 2 square root of 2. All right, so now we just solve for x. Okay, we already know that x squared is equal to 9 over 16 y squared. Okay, so plugging in our y value, x squared is equal to 9 over 16 times 2 square root of 2 squared. Okay, so you have 4 times 2, which is 8. Okay, so that gives us x squared equals 9 over 2. Or x equals 3 over square root of 2, positive or negative, but x is greater than 0 also, so we're just going to use the positive. All right, so we have our x and we have our y. We're just going to plug those in. So f of 3 over square root of 2 and 2 square root of 2, we're going to plug those into our original function, our objective function. Move that up a little bit. There we go. Is equal to 4 times x, 3 over square root of 2, times y, which is 2 square root of 2. Square root of 2's cancel out, so you have 4 times 3 is 12, times 2 is 24. Okay, so that's the maximum area of our rectangle. Okay, considering that was the equation from when we first introduced it, so that would be your maximum area. All right. So if you are still writing, feel free to press pause. But we're going to go ahead and go to our next example. All right, so let's say, for example, we wanted to use Lagrange multipliers to find any extrema of the function f of xy is equal to x squared plus 3xy plus y squared, subject to the constraint x squared plus y squared is less than or equal to 1. Okay, so when they say any extrema, that means they want to know the minimum and the maximum. Okay? So we already know we want to maximize and or minimize our f of xy. So f of xy equals x squared plus 3xy plus y squared. And our constraint is our g of x, y, which is x squared plus y squared is less than or equal to 1. Oh, let me make sure that's a little clearer. Less than or equal to 1. Okay, now whenever you have this less than or equal to 1, you have 2 cases that you have to think about. Okay, so we're just going to draw a little line here. Try to make that as down the middle as I can. There we go. That's a little too far, but it's okay. Okay, now case 1 is on the circle. And that just means that your constraint is x squared plus y squared equals 1. Now, inside the circle is when your constraint is x squared plus y squared is less than 1. So inside the circle. All right. So we're going to do our case 1 first, which is on the circle. So we know that we have to find our f of x equals lambda g of x. Our f of y equals lambda partial g of y. And our constraint g of x y equals our constant. All right. So that means we have 2x. Oh, there we go. 2x plus 3y is our partial with respect to x. And our partial of g with respect to x times lambda is going to equal lambda times 2x. And our partial of f with respect to y is equal to 3x plus 2y is equal to lambda times our partial of g with respect to y, which is 2y. So lambda times 2y. And our constraint, our g of xy equals c, is x squared plus y squared equals 1. Okay, so just like before, this one here, we're going to solve for lambda and plug into equation 2. Okay, now this second one, we're going to solve for x squared and plug into 3. You're going to solve for x squared and plug into equation 3. All right, so we're going to go ahead and do that right down here. Okay, so here, if we divide both sides by 2x, we see that lambda is equal to 1 plus 3y over 2x. Okay, so if we plug our lambda into equation 2, we get 3x plus 2y equals 1 plus 3y over 2x times 2y. Okay, and if we go ahead and solve that for x squared, that becomes x squared equals y squared. Okay, now that we have our x squared, we plug that into equation 3. So that means we have x squared plus y squared equals 1. Since x squared is equal to y squared, we have x squared plus x squared equals 1. Okay, so 2x squared equals 1. So x squared equals 1/2. So that means x is equal to plus or minus square root of 2 over 2. And same thing with the y squared. X squared plus y squared equals 1. So that means that y squared plus y squared equals 1. Or that y is equal to plus or minus square root of 2 over 2. Okay, so we have our x and we have our y. Okay, so we plug all combinations, where both positive, both negative, all into our original. Oh, there you go. f of xy. There we go. Okay, so let's say if we have our f of plus or minus square root of 2 over 2 plus or minus square root of 2 over 2. Now the thing about this one is, if you notice carefully, you have square root of 2 over 2 squared plus 3 times square root of 2 over 2 times square root of 2 over 2 plus square root of 2 over 2 squared. Whether you use both positive or both negative, if you have both negative, it will still come out positive. If you have both negative, it will come out positive. If you have both negative, it will still come out positive. So this one you can use for the same sign. Okay? So that will give us 2 over 4 plus 2 over 4 times 3, which is 6 over 4, plus 2 over 4. Okay, so that's equal to 10 over 4, which is 5 over 2. All right, so that's with the same signs. If both are positive, both are negative, we'd end up with that same answer. Okay, so now if the signs are different, since they're both the same value, you can do one positive and one negative. We just draw a little line separating that. Plus or minus square root of 2 over 2, plus or minus square root of 2 over 2. Different signs. Okay, so one's positive and one's negative. Okay, so that will equal, let's say if we make x positive and y negative. Square root of 2 over 2 squared plus 3 times square root of 2 over 2 times negative square root of 2 over 2 plus negative square root of 2 over 2 squared. Okay, so if you see here, if you make one positive and one negative, it doesn't matter if it's x or y. If x is positive, then you have positive here, it doesn't matter. The only time it's going to be different is right in the middle where one's positive and one's negative, but you'll get the same answer either way. Okay, so we end up with 2 over 4. Oops, straighten that out. Plus, you have 4, actually it's going to be negative. You have negative 2 over 4, so 3 times negative 2 over 4, plus positive 2 over 4, since negative times negative is positive. Okay, so it ends up being 2 over 4 minus 6 over 4, plus 2 over 4 is equal to negative 1/2. Okay, so far, this is our maximum value, and that's our minimum. Okay, so now for case 2, which is inside the circle, if you're writing, we still have to scroll back up. So if you're writing, feel free to press pause and finish this up. All right. Now, inside the circle, since we can't really use our constraint for less than, we can only use our constraint for equal to. Inside the circle, remember, it's an open, since it's less than and not equal to, that 1 is an open circle, an open region rather. Okay. X squared plus y squared less than 1 is an open region. All right. Okay, so since you have that open region, if you remember, you can always just solve for using the gradient formula. Okay, partial with respect to x, so you have 2x plus 3y. Well, we already figured it out over here. 2x plus 3y. We want to find where that is equal to 0. Now, partial with respect to y, we have 3x plus 2y. We want to find out where that is equal to 0. So if we use the system of linear equations in two variables, we'll see that x equals 0 and y equals 0. Using systems of linear equations to solve it. Okay, so we know x equals 0 and y is equal to 0. Now we have to find our second derivatives. Second with respect of f with respect to x. Okay, so that would be 2, since you already had 2x, and this would be a constant, so that's just 2. Second partial with respect to y, that would be 3. So that's that right there. And we know our partial of x with respect to y after, that would just become 3. So partial of x here, that with respect to y would just be 3. Alright, so we know our formula. Second derivative of x times the second partial with respect to y minus partial with respect to x, y squared. Alright, so if we plug everything in, our second partial with respect to x is 2. Second partial with respect to y is 3. Minus partial with respect to x, then y is 3, so 3 squared, which is 6 minus 9, which is negative 3. We know our d is equal to negative 3, which is less than 0. Okay, so since d is less than 0, we know that 0, 0, 0 is a saddle point. Okay, which means no minimum and no maximum. Okay, so really combining these two sides, since there's no minimum or maximum here, you have a max here and your minimum there. So your maximum is equal to 5 over 2 at plus or minus square root of 2 over 2 plus or minus square root of 2 over 2. And your minimum is equal to negative 1/2 at plus or minus square root of 2 over 2 plus or minus square root of 2 over 2. Oops. Okay, so we have our minimum and our maximum. All right, so if you are still writing, feel free to press pause, but we're going to go ahead and move on to our next example. Okay, so let's say for this example, we want to, actually with this example, Lagrange with 3 variables. Okay, so in this case, the approach is pretty much the same. So let's say if we want to use Lagrange multipliers to find the minimum for, let's say, f of x, y, z, in this case, is equal to x squared plus y squared plus z squared, constrained, if I could put that up there, by x plus y plus z minus 6 equals 0, and assuming x is greater than 0, y is greater than 0, and z is greater than 0. Alright. So now, just like before, we have our partial of f with respect to x equal lambda times our partial of g with respect to x. We have partial of f with respect to y is equal to lambda times our partial of g with respect to y. Also, adding in our partial of f with respect to z is equal to lambda times our partial of z. And we also have our constraint, which is g of x, y, z equals c. Okay, so it starts off pretty much the same way. Okay, so if we do all of these, our partial of f with respect to x is 2x. And we have lambda times our partial of g with respect to x is just 1. So that's just lambda. Okay, so our partial of f with respect to y, 2y, equal lambda times our partial of g with respect to y, in this case is just 1. So it's 1 times lambda again. Okay, partial of f with respect to z is 2z, equals lambda times our partial of g with respect to z is just 1. So that's 1 times lambda again. Okay. Now if you look here, if you have lambda equals 2x, lambda equals 2y, and lambda equals 2z, that just means 2x equals 2y equals 2z, or x equals y equals z. Okay, so that makes things a whole lot easier. Why? Because if you look at your constraint, you have x plus y plus z equals 6. Okay. Now you don't have to do anything all that strange or strenuous. You see here, if x equals y equals z, then that means that x, y, and z all would have to equal 2. So that means x equals y equals z, and they all equal 2. Okay, so if we plug that in, we have f of 2, 2, 2. That's equal to 2 squared plus 2 squared plus 2 squared. 4, 4, 4 is just 12. Okay, which is your minimum. Alright, so you can see how sometimes it kind of works out for you, where it's not a whole lot of work. Okay, so if you are still writing, feel free to press pause, but we're going to go ahead and move on to our next example. There we go. Okay, so now we're going to look at Lagrange multipliers with 2 constraints. Okay, so far we've only had 1 constraint. Okay, and we have 2 constraints. That means your gradient of f is equal to lambda times your gradient of g plus the Greek letter mu as our scalar multiple times the gradient of h, where G and H are your constraints. Okay, so we know here that the gradients are not parallel. Okay, so let's say for our example here, what if we use Lagrange multipliers? To find the maximum, clean that up a little, find the maximum of, let's say f of x, y, z equals xy plus yz with the constraint x plus 2y equals 6 and x minus 3z equals 0. Okay, so we have two constraints here. Okay, so we're going to go ahead and start solving this one. Okay, now remember your formula here. You have the gradient of f is equal to lambda times the gradient of g plus mu times the gradient of h. Alright, so just to clarify, we're going to make this constraint our g of x, y, and this constraint our h of x, y. Okay. Now the gradient of f, remember that's the partial of f with respect to x times the I unit vector plus the partial of y times the j unit vector plus the partial of f with respect to z times the k unit vector. Okay, so that means our partial of f with respect to x, y is considered a constant, so that would be y times our I unit vector plus partial with respect to y of f, that would be x plus z times your j vector plus partial of f with respect to z, that would just be a constant, so that would disappear. So that would just leave you with y times your k vector. So now we find the gradient of our g of xy. Okay, remember that's just partial of g with respect to x times your I vector plus the partial of g with respect to y times your j vector. Oh, plus the partial of g with respect to z times your k vector. Almost forgot that last one. Okay, so that will equal the partial of g with respect to x is equal to 1. So that's 1 times I, which is just I, plus the partial of g with respect to y, that's just 2. So you have 2 times your j vector. You have no z, so pretty much it's just all constant, so that would just be 0. Alright, so now we get the gradient of our h. So that will equal the partial with respect to x times I plus the partial with respect to y times j plus the partial with respect to z times k. Okay, so that will equal the partial of h with respect to x is just 1. So that's 1 times the I vector, or just I, plus partial with respect to y. There is no y, so that's just all constant. partial with respect to z is just -3, so that's -3 times your k vector. All right. Now, if you remember your formula, right up here, that the gradient of f is equal to lambda times the gradient of g plus mu times the gradient of h. Okay, so our gradient of f, you have that right there. So you have y times your I vector plus x plus z times your j vector plus y times your k vector. Let me clean that up a little bit. Is equal to lambda times your gradient of g, so that's lambda times I vector plus 2j vector plus mu times your gradient of h, which is I minus 3 times your k vector. Okay, so if we go ahead and distribute those, we will end up with, our left stays the same. You have y times your I vector plus x plus z times your j vector plus y times your k vector is equal to, you have lambda times I and mu times I. So you end up with lambda plus mu times I. Okay. Now for your j vector, you have 2 lambda j, but you don't have one here, so you have plus 2 lambda times your j vector plus, for your k vector, you don't have a k vector here, but you have -3 mu here. So you have -3 mu times your k vector. Okay. Now the only way these can be equal is if this multiple of the I vector equals this multiple of the I vector. Okay, so that means that y would have to equal lambda plus mu. Okay. So that means this multiple of the j vector would have to equal this multiple of the j vector. So that means also that x plus z would have to equal 2 lambda. Oops. There we go. Now this k multiple of the k vector would have to equal this one. So y would have to equal -3 mu. So y would equal -3 mu. Okay. Remember, the overall goal is to one by one get rid of all of your lambdas and mu's. Okay. So with these two, the first and the third equation, you have y equals lambda plus mu, and y is equal to -3 mu. So that means you just have to solve lambda plus mu equals -3 mu. So if we solve that for mu, and then substitute. Okay. So if we subtract mu from both sides, we have -4 mu, then divide both sides by -4, we end up with mu equals lambda over -4. Okay, so we already know that since y is equal to 3 lambda over 4, remember -3, let's put that right here. So we know that lambda is equal to 4y over 3. Okay? remember, all we did here was plug in the mu here. And you're going to plug it in here and end up with the same thing. So once you solve for your mu and you plug it in, this is what you end up with. Okay. Now we get the same thing here because we now solve for lambda. That means x plus z is equal to 2 times lambda, or 2 times 4y over 3. So that means x plus z is equal to 8y over 3. Okay. So here we have a y that we have solved for. We have an x plus z that we have solved for. So we're getting closer and closer. All right, so now if you look at your constraints, you have x plus 2y equals 6. Which means if you solve for y, you have y equals 3 minus x over 2. Okay. And if you look at x minus 3z equals 0, that means that z is equal to x over 3. Okay, so we're getting there little by little by little. Okay, we're slowly getting rid of it. You look at these three, x plus z equals 8y over 3. We don't have any more lambdas or mu's. Okay, so now we can start working through them and solving for our x, our y, and our z. Okay. So we know that x plus z equals 8y over 3. Okay. Since we know that z is equal to x over 3, that means x plus x over 3 is equal to 8 over 3 times y, so 8 over 3 times 3 minus x over 2. Okay, so all x terms. So once you solve for x here, you'll end up with x equals 3. Okay, so little by little it's starting to work out. Okay, so we know that y is equal to 3 minus x over 2. We know that x is equal to 3, so y is equal to 3 minus 3 over 2. Okay, so if you change that to 6 over 2, 6 minus 3 is 3. So you end up with y equals 3 over 2. Okay, so now, just solving for our z, we know that z is equal to x over 3. So z is equal to x over 3. So that means z is equal to 3 over 3, or z is equal to 1. Okay, so we found our maximum value. All right, so hopefully this has made some sense, and I will see you on the next video.